Most of you know me, so it's almost not worth introducing myself. I'm David Milne, and I'm a vice chair of Greater Manchester Humanists. We hold this event every year, and we've been doing it for. Where is John Koss? John, how many years have we been doing this? Roughly. Go on, give us. Oh no, it's more than that, John. I've been doing it 12, and it was after you, wasn't it? So it must be at least 20 years. Anyway, long story short, you don't want to hear about me because I'm incredibly boring, but I am genuinely very excited to have this evening Dr. Alfredo Carpineti. And I said that really well too. It's Dr. Alfredo Carpineti. I mean, you can't say it with a Cockney accent, really, can you? So, Alfredo, ladies and gentlemen, please give a very warm welcome to our speaker tonight. It's going to be really exciting.
Thank you very much for having me, and happy Darwin Day. Darwin was born 217 years ago today, and I'm doing tonight something a little bit different from my usual, because I will talk a little bit about biology. And I know I'm a physicist, and physicists have the terrible habit of just wanting to solve every other discipline. Philosophy, physicists can solve philosophy. Art, physicists can solve art. At the end of the day, everything is physics. But I promise that I will not go in guns blazing to solve the rest of human knowledge. So, who am I? My name is Alfredo. I'm an astrophysicist, and I work as a science journalist. I also the chair and founder of Pride in STEM, which is a UK-based LGBTQI+ charity for people in science, technology, engineering, and maths. And I am an author, and my book Invisible Rainbows is coming out in May. And you can ask me about that later, but there should be some bookmarks on the table out. So, let there be light. And I was quite proud that I put citation needed. This is pretty much the only two, this and another bits of humor in the talk. And my husband was very much like, it's not supposed to be a very serious talk. Why are you putting this? I was like, this is funny, it's good. But yes, whatever we consider light in a scientific sense or light in a philosophical sense, life and light has always been quite connected. Obviously, we see it, that is the first thing that happens in the Bible, but clearly our ancestors, once they started to realize that they could use the stars and the cycle of the sun to work out how to grow things and changing of the season, they must have started having this idea that there was something profound that was linking life and light, even though they might not have had a perfectly clear idea. But to be honest, we also struggling to get a perfectly clear idea of how life and light are connected until very recently. But first, we need to discuss two big questions and two very complicated questions. The first one is, what is life? And I'm gonna say that we have several good definitions. This is one that I personally prefer. There are one that talk about there needs to be an organism that can grow and change and adapt following Darwinian evolution. I like these 7 little characteristics, and then I'll tell you why this little guy doesn't fit that. So what are those? Homeostasis means that they have an internal balancing system. So the things internal of this, whatever we call life, is balance. Organization means that I have structures. Metabolism means that they consume and produce energy. growth, self-explanatory, they can change, adapt. That is where the Darwinian evolution comes in. The response to stimuli, it means that they can interact with the environment and they can reproduce. A lot of this, we can make a very simple example, crystals. They can grow, sometimes they respond to stimuli, but they are not a form of life. They are something that we would never consider life, even though at fundamental level it's a self-replicating molecule, just like DNA is. And this little guy is a guy that we love to hate because it's SARS-CoV-2, the virus that is responsible for COVID. And viruses are not considered life. And why not? Because despite they have genetic material, the only way for them to reproduce is to use the apparatus, the organization, and the living structure of other living beings. And I feel that this is a fair distinction, but there are a lot of people, biologists, philosophers, that have a very good argument about expanding it to include viruses, or considering that maybe we might encounter life elsewhere in the universe that doesn't fit with these 7 parameters, but we could recognize very much as life. What I feel as a physicist that is even a tad scarier is that there might be life that we wouldn't recognize simply because our one example of life on this planet is maybe very narrow. The other big question is, what is light? And I feel that as a physicist we have a better concept of that. But for thousands of years we have been debating of its nature until we truly reach a revolutionary answer. So, the very basic, very broad definition, light is an electromagnetic radiation, is an interaction between electric and magnetic field that moves through space. It can move through vacuum, and it connects charged particles, and we're constantly, even us right now, we're emitting light. We are emitting infrared, which is what we normally call heat. And it is absolutely the reason why we're here, but we will have to get there in a very long-winded way. We have a wonderful poster about the ages of the universe, and pretty much we're going to go all the way back up there. Why it has been debated for thousands of years? Because scientists, philosopher, natural philosopher, pretty much anyone had very different ideas of what light was. Light was considered a particle because it moves in a straight line. If you see the light reflecting on a mirror, you would assume there needs to be something that bounces, just like a particle would. But light was also seen as a wave. You can see here something called diffraction. So that was actually the experiment in the 1800s that convinced people, saying, no, light must be a wave, because the double slit experiment, if you have light coming in, it produces this curve, and the only way to curve things is if it is a wave. And at the same time, they also started to realize that light was somewhat related to electromagnetism. So thousands of years got almost an answer, until the answer was found to be extremely limited, which should be like probably the tagline of science. The answer is extremely limited for now. Because scientists and Albert Einstein realized that light is both a particle and a wave. The properties that people have seen, that life bounces off, were real. People could see that. Something very, very, I think I love, that is very powerful about the fact that light moves in a straight line. Who here has seen a rainbow? I'm assuming all of you. Has any of you, have you, I don't know, you're here with a partner or a friend, have you seen a rainbow at the same time? Together? Few nodding. And I'm gonna tell you, you didn't see the same rainbow at the same time. Because each rainbow is unique to our very eyes. Because a rainbow is just a trick of the light. It is sunlight passing through rain droplets. The rain droplets split the white sunlight into its constituent colors. And it's that specific ray of light that gets split and is moving in a straight line all the way to our eyes. So if you have your significant other, a friend, someone else standing right next to you, they're still not seeing the same rainbow. So every rainbow that you have ever seen, they were just for you, unique in the universe. But because of that splitting, all the other properties of life, of this waviness, Albert Einstein managed to connect the two and realize that it needs to be both. It needs to be something that is, for us, inconceivable. That one thing was actually two things that could both be a particle and a wave. The Einstein discovery is called the photoelectric effect, that you might be like, okay, why is that important? Well, if you got a smartphone, you are using the photoelectric effect every time you touch, and it is used in a lot of other physical and technological application. And it's pretty much also in solar panels. Light comes in, it produces an effect on a certain material, the material releases electrons and you have a little circuit. And that was the beginning of quantum mechanics. Suddenly, light was we started to see how light was interacting with matter in a deeper way. It proved that reality is fundamentally probabilistic, that it's something absolutely absurd, because, to be honest, Einstein didn't actually believe that. This is why he said that God doesn't play dice with the universe, and he actually didn't also believe in God. They meant God as some sort of natural order. But actually, the natural order does play dice with the universe. Everything is probabilistic, and we do not experience it simply because at our level, all the complication of quantum mechanics are even out. And so what we experience is a world that we call the classical physics, that works in a very deterministic way. But ultimately, that is not what reality is. And it was fundamental that we discover light to starting to see death. Now, the thing is that things can exist in superposition. You probably heard about the quantum cat, a cat that can make a quantum cat experiment, a thought experiment. No cat is harmed in the making of this experiment, but if you put a poison that is activated by a quantum effects of some sort, then the cat, you put the cat in the box next to the poison, then the cat could be both alive and dead. Why? Because the quantum effect could be in its activated state and non-activated state. And until you check, until you go and look and you observe the quantum system, the two things exist at the same time, and both of them are true. And this is something, it's important. The quantum is not, the cat is not dead or alive, is dead and alive. And that is crucial. And all it comes down to understand that light existed as a particle and a wave, because then it led to understand that also matter, every single bits of matter that make us, but even our whole bodies technically could be considered as a particle and as a wave. It's just that, I don't know, if we were to run towards a double slit experiment, we will not split quite like that. Now, once we started realizing that there was more to the universe, we started to realize that the two major forces that we all have experienced, gravity and electromagnetism, were actually half of what the universe had out there. The other two were a lot more fundamental and yet very, very important. The strong nuclear force is what binds the nucleus of our atoms together, so definitely very important. The weak nuclear force is usually the one that is abandoned because, oh, it's very peculiar. It has to do with some radioactive decay. But just to give you an example that you can say, okay, gravity, electromagnetism pretty much, in most of our technology or in our fridge magnets at home, a strong nuclear force, it keeps all our atoms together. That's good that we have it. What about nuclear force? Is there an example that doesn't include a nuclear reactor or the sun? Yes, there is. If you have bananas in your home that have some radioactive potassium, very safe. Literally, you need to. There was a calculation some years ago that you would die more by dehydration by the number of bananas that you need to eat to get the radioactive poisoning. It's something like millions of bananas to get radioactive poisoning from bananas. So completely safe. But the radioactivity in the potassium in the bananas is mediated by the weak nuclear force that brings some tiny particles and make the potassium decay, and it's very, very cool. Also, the reason why we do not experience the strong nuclear force and the weak nuclear force at our level is because they have a very, very short range, even though they are much stronger than gravity. So why is gravity something that we feel so much? Is because the Earth is very big when it comes to us, very small when it comes to the rest, but we shall see that in a minute. Now, I was asked by David to talk about quantum electrodynamics, and I will be very, very gentle. We're not going to go too much into the maths and even the physics of it. But once we started to realizing that the universe was quantistic, that reality was quantistic, we had to start working out exactly what that meant. And that meant a fundamental connection between matter and light. As I mentioned, light mediates the electromagnetic force. So between charged particles, there is light. There are these things called virtual particles. So light is carried by photons. Those are the particles of light. And in the electrons and protons that make up your atoms, you can imagine electrons to be like little planets going around the protons, although that is not exactly correct. We can picture it like that for a second. And you have photons jumping between the two. But those photons are virtual, which just means that we cannot exactly see them. We just need to assume that they're there, because otherwise all our mathematical setup, all the physics that we have built to make our model of reality works doesn't work anymore. So you would need to just assume like, okay, there are these particles that exist, but we don't know and we cannot find out. There's sort of ways to find out. So some are very complicated, like you can have a black hole and you can find some virtual particles. I do not recommend being near a black hole and getting some virtual particle like that. But you can also do some weird physical experiment even in space that tells you, okay, this virtual particle exists. And you're doing quantum electrodynamics right now. As I mentioned, you are emitting heat, and heat is infrared photons. And the vibration of the molecules in your body is producing these electromagnetic changes. And so you're emitting heat. And so you are doing quantum electrodynamics. We don't understand it. Let's me put hands forward and say, no. It's not, I think, on the planet, understanding quantum mechanics is pretty much a taboo. Like, no physicist will say, no, I don't understand it. So it's just because it's so complicated. We know some of how some of it works, we know how some of the maths work, but truly understanding the mechanics, maybe it's even beyond our species. So we are doing pretty good. We understand a good chunk of it, but we're still not entirely sure what all of it means. But from quantum electrodynamics, we go to the fundamental process that keep us alive, and that is photosynthesis. We are very much in debt with any photosynthetic organism on the planet. Most of them, we have here lovely plants, but most of the oxygen is not from plants, it's from cyanobacteria, which we will meet in just 1 or 2 slides. And it's one of the big questions that the overlap between physics and biology has been asking is how much quantum magic, let's say, how much quantum mechanics is actually happening when plants do photosynthesis. And the answer is currently unclear because it's very, very difficult to study photosynthesis in a real-life organism. We think that should be a good chunk. And the thing that we suspect that should be a good chunk is because photosynthesis is extremely efficient. So almost every ray of sunlight that gets into the chloroplast, where the photosynthesis happens, is used to make photosynthesis. If you have any kind of engineering background, you know that an efficiency of 100% is like beyond anything that it's like mechanical wise. You know that that is not something that you can do. And it's very, very, very peculiar that a system like this would work at a level of particles and atoms without having a quantum effect. But what is that quantum effect? And that is the biggest question. One idea, and I'm gonna say that there are plenty of people that are skeptical, but many others are like, this must be it, is this idea of, wrong side, of quantum coherence. I've mentioned the idea of the quantum cat, that is dead and alive. The quantum coherence means that the state is stable. Like your quantum cat is very easy to check if, to be honest, if you shake the box, it'll probably meow or something. Or if you shake the box, you break the vial of poison without the need of quantum mechanics and you kill the cat. So the quantum coherence is a state that remains stable. And it's something that a lot of people working on the next big leap forward for computer called quantum computing are trying to achieve, and they're trying to keep a bunch of atoms in this quantum coherence for fractions of a second, and they get sometimes so few milliseconds are like, oh, we have broken a record, we had quantum coherence for milliseconds. And if this idea of quantum coherence in plants is correct, it's just telling you like, plants do it all the time, plants very stable, it works for plants. How? We don't know. If we could work it out, revolutionary, but we don't know yet. To try and work out these steps of photosynthesis, of how it works, we're actually using the most powerful laser to pretty much get snapshot of the molecules changing and influencing whatever is going on in the chloroplast, like a little snapshot at a time. And this powerful laser is so bright that it emits X-rays. It's an X-ray laser, so don't think it's like a little pointer. It's an enormous machine that needs to accelerate first electrons, and that accelerated electron produce these X-rays, and they're trying to get like this fraction of a second of events happening in particular photosynthetic organism, just to try and get exactly how those steps work, to potentially open a door to a whole new realm of understanding of life. And here are our microscopic Prometheus. Those are the cyanobacteria that I was mentioning. They produce a lot of oxygen here, but more importantly, they were the first organism, roughly here, that brought oxygen to the planet. And this is why I call them Prometheus, because the way non-photosynthetic organisms use oxygen, like us, we create a little combustion in all our cells. Everything that we, the process that we get energy is literally a little fire. There's a little fire in all of our cells. And at the time, around 2.4 billion years ago, we had a lot of different organisms on the planet that were using sunlight in different ways for energy. But these organisms decided to have a byproduct. They will grab in the carbon dioxide from the atmosphere, use the sunlight to split it, and they would just throw out the oxygen, which led to probably the greatest extinction event that our planet ever experienced, because maybe up to 99.5% of all living organisms at the time went extinct. But, well, we're here thanks to them, so good for us. And it's very crucial that for as much as we appreciate what the ancestor of cyanobacteria had done, they were not only organisms using light. They were only the first to work out that they could produce oxygen and give them an advantage, because the process of photosynthesis gave them more energy. And with more energy, all the stuff that we said about life, all those processes became more easy. And that's bringing us to pretty much up there. Why is Earth special? As far as we know, Earth is the only non-habitable world, and we can have a discussion. You can ask questions later if we think that there are other places that are possible for life, or where we should look, or where we are planning to look, etc. As I said, it is limited biased view, because we have one example, so we cannot be certain that these characteristics are crucial. But we think that being the right distance from the sun is good, because allowed us Earth to have a water cycle. So water exists as ice, water vapor, and liquid. The liquid is very good for microorganisms to form, but the ice and the water vapor meant that there was rain and things change, and there was this motion of things. We also have a lot of organic material on the planet, a lot of carbon, and for as much that there are possibility and scenario in which we consider that maybe silicon-based life could evolve, we think the carbon is the best to create long chains of molecules. And as far as we can tell, with us, long chains of molecules is the most important things. It's found in DNA, in proteins, in lipids, which is just a general term for fats. All of them are all good and all crucial to life. The Earth has a strong magnetic field protecting us from some of the events that are, especially extremely energetic events released by the sun, but also cosmic rays from supernovae and other things. And we'll see that things can still mess with our atmosphere, but this magnetic field protects us as an atmosphere that also protects us, and as plate tectonics that, yes, we are definitely not thrilled, especially if, like me, you come from an area with earthquakes and volcanoes. and a super volcano that who knows when could go off. It's scary, but also plate tectonic meant that there was motion of elements and material throughout the planet. And we also have a pretty weird and very large moon, a stabilizing moon that has helped the planet and life on it thrive. And so the question is, are all of these requirements or are things that help us? We don't know. What we know is that the fundamental building blocks of the molecules that are important, the building blocks of sugars, of proteins, the amino acid, can be found in space in a lot of different environments. This is called HL Tauri, and it's a baby planetary system. You can see, hopefully the light is not too bright, but you can see dark rings in this nice little image in microwave millimeters wavelength. Each dark gap tells us there is a planet being born, or maybe a small object being born, and is cleaning up the orbit. A little bit, it looks a little bit like an LP. And the grooves are just little planets grabbing things, grabbing some materials and growing. But there's also something very exciting beyond the planets, is there are molecules being formed by that star, and in all the other systems that we see similar, there are molecules being formed by that star, and molecules that are complicated. And I will give you a few places and a few examples. In comets, we had found organic materials. We had found amino acid. That is the gorgeous Hale-Bopp, the great comet of 1997. I hope many of you will remember that. And we had found very interesting molecules in the dust of comets. This is asteroid Bennu. We got a sample from asteroid Bennu in 2023, and we had found that 15 of the 22 fundamental amino acid, are there are, I think, like something like 500 amino acid, but the 22 fundamental amino acid are those that are fundamental for life on Earth. Humans only use 20 of those 22. 15 of them has been found on asteroid Bennu. And asteroid Bennu is just a pile of rock in space. It is also the most dangerous asteroid on Earth. It has a chance in 1,700 to hit our planet on the 24th of September, 284. So not for us to worry. But asteroid Bennu is just a pile of dry rocks in the middle of space. Why has it got this amino acid? They must have formed in interstellar space, and they've just been, or they must have formed on its asteroid Bennu form from the collision of a larger body that released it. So either in interstellar space or on in the specific planetoid, there must have been the right condition for the building blocks of life. So can we really consider Earth a special place? Or should we just consider that we have some special condition where those building blocks can then thrive? And this is one of my favorite. This is Sagittarius B2. At least you can think, okay, Bennu comets, they're in the solar system where things are nice and easy. This is a gas cloud made of mostly hydrogen, very close to the center of the Milky Way, where Sagittarius A star, the supermassive black holes at the center of our galaxy, resides. It has also a lot of the precursor to amino acid, which are the building blocks of proteins, and it has ethyl formate. And now you're like, okay, who cares about ethyl formate? What is even ethyl formate? Well, I can be certain that you have either smelled it or you tasted it, because ethyl formate is responsible for the smell of rum and about half of the taste of raspberry and a third of the taste of strawberries. Ethyl formate as very chemically named for a molecule that is found in a lot of plants on Earth. And we then need to wonder, what is it doing in a cloud 26,000 light years from our planet? Again, maybe all these building blocks, all these molecules that we see as fundamental for life on Earth can just form everywhere. And if they form in a cloud, in the middle of nothing, it just means that light might have produced the right condition for that molecules to form. But before we get to those, we need to talk about a little bit more chemistry. Because at the beginning, as we will see when we reach the Big Bang, the universe only had hydrogen, some helium, and truly a sprinkling of lithium. I can't even tell you that the lithium in your phone battery is all from the Big Bang. No, a lot of it is from other stellar processes. We'll see that in a second. And all the other elements, all the elements that form us, especially the carbon, the oxygen, the calcium in our bones, must have formed throughout the different phases in the life of stars that we will see in a second. And this is the beautiful Crab Nebula, which is a supernova remnant. And those supernova are the reason why the elements have been spread, but we'll get there. So this is the life cycle of a star. You start with a big cloud of gas, just like Sagittarius B2, where we found the ethyl formate. That is a great place for star to form. But something that is always found a little bit counterintuitive is for stars to form, for stars to start nuclear fusion, there needs to be very cold, because those big clouds of gas need to collapse. And they need to condense, and so they need to be cold, and then gravity takes over, it combines things, the pressure gets higher, the temperature gets higher, and bam, you have nuclear fusion and you have stars. Average stars like our sun, they will just spend a long time shining. Our sun is middle age, been shining for about 5 billion years, and will have another 5 billion years of just shining as it is. And then it will run out of that hydrogen at the core, because its core, by fusing hydrogen, is producing helium, and it will swell up into a red giant. But it's not massive enough to do anything else after the red giant, so its core will collapse in a white dwarf, and it will release its outer layer in what we call a planetary nebula, which is very confusing because it has nothing to do with planets. It's just because to astronomers 200 years ago, it looked round like a planet, so like, oh, planetary nebula. If you instead have massive stars, that's where things get interesting, because the red supergiant will have fusing the helium into carbon oxygen, and then that carbon and oxygen will be fused in other heavier elements, and so on and so forth until you get to iron. Eventually the star will have a core of iron, and you cannot use nuclear fusion, you cannot fuse two iron atoms and get energy out. So there is no more energy coming from the center of the star. And what happens is that the outer layer of the star starts collapsing back in towards the core of the star. And that is a very, very violent event, which is we call a supernova. And that spreads out, as we've seen with the Crab Nebula, and throws all those elements that have been produced by the stars out into the galaxy. And the supernova has two possible outcomes. You can produce a neutron star, which is a very dense, very small object, pretty much the mass of our sun, 1.5 times the mass of our sun, but 10 kilometers across. so would easily fit into Manchester. The problem is 1 teaspoon of neutron star is roughly the weight of 900 of the Great Pyramids of Egypt. Which is a lot, I know, you can see that I have very strong arms, this is why I can lift it. But yeah, that is an extreme object. And the other thing is a black hole. But the neutron star is going to be important because we're going to see that in the next slide. I switch them around, but we are going to see that not all elements are produced inside a neutron star, inside a regular star. And here is another view of the Crab Nebula, and I love this view because it combines the previous one, which was Hubble, plus some infrared from Spitzer, plus Chandra in X-rays, the X-rays, the purple one, and show that yes, there's all this stuff that is being thrown out, but at the center there's still a neutron star being very active and is still doing things, still helping spread these very important elements into the universe. And here is the slide that I wanted, and is the periodic table, and it tells you where things come from. So the Big Bang, you have hydrogen and helium, and a little bit, you can see a little stripe of lithium, and then you have massive stars, you form things that are very important to us, oxygen, fluorine, other elements, magnesium, sodium, chlorine, very, very important. Then you have things like dying low mass star, like the sun would free some carbon into the universe, and some nitrogen, which is the main component of our atmosphere. But there are things that can only be achieved through the collision of those neutron stars. And there are stuff that you might be like, okay, it's mostly decoration, gold, platinum, they're all achieved through that. But for our own body, something that is very important that is produced in the merging of neutron star is iodine, which balance our metabolism. And I just want to give you a little bit of maybe terror, hopefully not too much terror, but just an idea of what that collision between neutron star does beyond producing some pretty important elements on the periodic table. This is the brightest gamma ray burst that has ever been recorded. It's called BOAT because it's brightest of all time. Sometimes astrophysicists don't really have much imagination in namings. And you can see here very much sped up. Looks just like a little flash. But BOAT was from, we think, an extremely powerful supernova. Gamma ray bursts can be produced by neutron star collision or very powerful supernova that end up producing the neutron stars or the black holes. And we measured it that it came from about 2 billion light years away. But the light of this event was so intense that when it reached Earth, it ionized the atmosphere. And this electric charge, ionized means that it freed some of the atoms in the atmosphere from its electrons, so they were all electrically charged. And this made the atmosphere ring like a bell for 12 hours. So there is an explosion in a galaxy 2 billion light years that is affecting the atmosphere of our planet for 12 hours. And I absolutely love that because it is one of these incredible events in the universe that we wouldn't know that were happening out there if we weren't looking at the universe in other wavelengths. And we only actually study the universe in gamma rays because gamma rays satellites were sent up in the 70s to make sure that nobody was using nuclear weapons where they shouldn't. And then they started to see gamma ray flashes from space, and are like, that is weird. We shouldn't have nuclear weapons exploding in space. And started realizing that there are incredible events that are fundamental for the chemical makeup of life on Earth that are happening all over the universe and continue to marginally, fortunately, affect our planet's atmosphere. And we are moving quickly up our list, going towards the Big Bang, because we had the stars that have been producing those neutron star colliding and everything, but as I said, the first stars were made only mostly by hydrogen and a bit of helium, and yet it's just a lot of assumption. We know that there is a point in the universe that becomes enriched or polluted with all the elements that make us. And polluted is the technical term that is being used. I'm not being flippant about it. I'm very, very much happy to be alive on a planet with pizza. So there is a moment in the universe that all those elements are starting to be created, especially the carbon and the oxygen. And if I were to give this talk, if I been invited a couple of years ago, I would we know, should be around 200, maybe 300 million years after the Big Bang. Now I have, not just me, but everyone's been maybe it's about 150 million years, because we found galaxies very, very far away, and this is the farthest galaxy known yet, that exists at a time that we didn't think the galaxy were existing, and already show sign of being rich with those elements. We have never seen these first stars. The first population of stars continues to be an unknown. We have some possible hints, but we've not seen them. This is one of the very first galaxy. It's called MUM Z14. Z14 is just a measurement of distance. MUM doesn't stand for mother, but stands for mirage or miracle. And is the specific survey trying to work out if these things that looks very distant in this data are actually there. And this is called the cosmic miracle, because it doesn't make sense why it exists back then, 280 million years after the Big Bang, and it has already some of the more evolved elements that we expect later in the history of the universe, which tells us that even though, as physicists, as I said, we think we can solve everything, we can solve biology, it's photosynthesis, all quantum mechanics, we can solve this. In our own little field in astronomy, we were pretty convinced that we knew everything, that we would use JWST, brilliant new telescope, looking infrared, we'll find the first galaxies, and we will see that they don't have any carbon, they do not have any oxygen, and we'll find those first stars and say, that is the moment that they go supernova, they start releasing those. And we have not found those yet, which is both humbling, but also a very juicy cosmic mystery. There is something else for us to look for. There is something that we are missing, not getting. It's a very humbling experience. And we get to the oldest light in the universe. This is the cosmic microwave background. This is the first time in the history of the universe, around 380,000 years after the Big Bang, that the universe had expanded enough so that matter was cool enough for the light to be free. Before, the universe was so hot and the light was so energetic that it couldn't escape matter. There was this constant relationship between matter and light. I mentioned the concept of ionization, like the gamma rays that hit our atmosphere and stripped the atom of their electrons. Is the same process here. Light is trapped by matter, matter is trapped by light. And up to that point is they are one and the same. They are connected at a fundamental level. But in this map, in this slide, there is a map of the universe that it will be. In general, we tend to translate the cosmic microwave background to a temperature map. The universe, based on that idea, is at a temperature of just a few degrees above absolute zero. The differences between the darkest blue and the brightest red is 1/10,000 of a degree. Tiny, tiny difference, which tells us something very important and fundamental about the universe. The universe is roughly the same everywhere and in every direction. And that is very, very important, because we like to think that, our physics work here should also work on Andromeda, should also work on a galaxy that is 13 billion, 14 billion, 30 billion light years away. That is very important. This is the case. But these tiny differences will eventually shape the universe. These tiny differences meant that some regions would get a little bit more matter, and some regions will get a little less matter. And with that, the universe started to organize in something that we call the cosmic webs. The cosmic web, the galaxies and cluster of galaxies are in this. The web, don't think of a nice, European spider and kind of lines. Think of one of those bushes in Australia covered in webs. Absolutely covered. That is the cosmic web. There are strands and filaments going in three dimensions, and along those nodes, the biggest clusters of galaxies and galaxies all along the filaments, and all of that is pretty much already put in place here in the oldest light in the universe. And finally, we get to the very beginning. Those atoms that trapped light for almost 400,000 years took minutes to form after the Big Bang. The first particles took seconds, but it's at the very instances of the universe, a number so small that I decided it was not even worth putting it down here, because it's so tiny. All those forces that I mentioned, gravity, electromagnetism, the strong and weak nuclear force, were only one interaction. So from everything, from all the same forces, for all the interaction, and from everything else, from all the energy that it was there, came all the light in the universe and all the matter in the universe. And this is why life and light are unavoidably linked. We have taken a journey, a very quick journey, across our 13.8 billion years or so. There is I think I've used some very simplistic biology and some very complex physics, but both of them go hand in hand. Our understanding from truly the very beginning of our civilization, of the connection between light and space to the season, to growing and culture eventually, it's very important. We could recognize immediately that light and life had a connection. We now know how much light has played a fundamental role in matter. A sculpted very molecule that makes us and our planet. We've seen it in the amino acids that are found on Bennu. We've seen it in the molecules in Sagittarius B2. We know that it goes even deeper, because without the stars, without the energy and light released by the stars, the fundamental atoms that make those molecules, that make us, would not exist. Light was there every step of the way to influence matter, and matter was influencing light. And we are eventually and ultimately the product of light meeting matter. And that is, for me, the secret of life and light. So thank you very much.
I am light, you are light, we're all light together. Isn't it wonderful? So it's a Q&A session now. If you have any comments, questions, please raise your hand and I'll give you a number. So you're number 1, you're number 2. Oh, you're all boys. 3, 4, right, you've got to remember your number, that's the game. Okay. If you're going to ask a question, be as precise as you can, and if you're going to make a comment, be as relatively brief as you can. Okay.
I've heard that there's next to no light and life if in the bottom of the Pacific and far away. So how does that affect the theory that when light is so minimal even on Earth in places?
So there are plenty of creatures that have evolved to use very little light. Some of the things you mentioned, they live near hydrothermal vents, so they use the heat of from hydrothermal vents are volcanic secondary volcanism, so just hot springs at the bottom of the ocean. And it is a very good question, and is one of the big uncertainty when we consider how can life exist on other planets. Those organisms, and some of them are very simple bacteria, some that are more complicated. There is a snail that has been able to learn to use some iron sulfide that comes out of these vents to make a sort of armor shell. It's very cool. And those are considered extremophiles. So they are organisms that can live in extreme environments like we couldn't. And question that some of these extremophiles can survive at space condition. And it's very interesting, but the question is, can they evolve to be extremophile in space condition, or they need to start in a place that is mild? And then evolution can take its course and lead them to be able to deal with no light, just based on chemicals or just using heat. And the question is an open one. We are uncertain of the answer because, again, we only have one example. If we were to go to Enceladus, which is this icy moon of Saturn, which we know has hydrothermal vents, we know that has complex chemistry, we don't know if it's got life. But imagine if we were to find life there, then we can say, okay, this is an icy moon with a crust of 20 kilometers. Maybe you do not need light as we intended sunlight to make it work. Maybe just the heat, internal heat of the planet, it's enough to be the right light for extremophile. If you don't find life there, then it's like, that question remains open. It's one of the problem with this kind of question that you can only prove it if you find something that agrees with your starting point. You cannot you cannot prove a negative in a way.
Thanks. Who's number 2?
Martin.
I think I've been living under misapprehension. When you went early on in your talk, you talked about the weak nuclear force. I always thought that was the force that held electrons in orbit around the atom, but I'm wrong there, am I?
Yeah, electrons are held by electromagnetic force because they are negatively charged, yeah. And atoms is made of protons, which are positively charged. Larger elements have protons and neutrons. Now, the thing that the strong nuclear force comes in because if you put all the protons together, yeah. They should repel because it's all positive. Instead, at a nucleus level, so if you remember, it was a very short range force, the strong nuclear force is a lot stronger than the electromagnetic force. But the things that keep the electrons around the nucleus is just plain and simple plain and simple. Once you get into quantum mechanics, nothing is plain and simple, but it is electromagnetism. There's, the weak nuclear force comes in the interaction between neutrinos, which is these ghostly particles that are also electrically neutral, and the atoms. You might have thought it because some of the radioactive decay mediated by the weak nuclear force release electrons, or the antimatter equivalent of the electron, which is the positron. So that's probably where I would assume where it come from.
Thank you.
You're welcome.
Number 3. Who was number 3? Oh, you're number 3, Peter. You are, Peter, number 3. Thank you.
Dr. Alfredo.
Yes.
Enjoyed your speech. Thank you very
you.
much. I would like to ask you a question. And Richard Dawkins has been asked this same question and could not answer it. However, he's a biologist, so of course he's not got the expertise that you have as an astrophysicist. So my question is, where did the universe come from?
Ooh.
Now, Lawrence Krauss wrote a book called Everything from Nothing. Now, can you explain to me, please, how you get something from nothing? You are an astrophysicist, and you know all about these things.
Yeah, and it's very much how much we do not know. So maybe I should have put, I told you I didn't put the number because I thought that it was going to be too tiny for us to comprehend. This moment when all the forces were one, that is the moment that our physics ceases to make sense. The concept of space and time only works from about 10 to the minus 32 seconds. So it's a 0 point, decimal point, another 1 second, roughly. That's the moment that our physics begins. So asking what was before the Big Bang doesn't make sense. Yes?
There is substantial disbelief among scientists that the Big Bang ever happened. And what they are now saying, and you will know this, I'm sure, what they're now saying is, we do not know what the Big Bang was, and we reserve judgment until we've got further information. Now, you know that, and you know that a lot of scientists do not believe in the Big Bang.
That a lot of scientists do not believe, I find it doubtful, just because of this picture. And this tells us that the universe used to be in a hot dense state roughly 13.8 billion years ago. There are some, to mention alternatives ideas, Roger Penrose, he believes that the universe is cyclical, to answer, to give a potential explanation for where the universe comes from. So it's something that the universe repeats itself over and over again. So the universe will expand, and at a certain point it will contract again in the Big Crunch, which just sounds like a candy bar. But again, I said, astrophysicists is not the most imaginative bunch. And after it contracts, it will bounce out again, the big bounce. And this is the idea of the cyclical universe. There are ideas of what could have been before, beyond the universe. They are not technically scientific words because, as I said, space and time starts after the Big Bang. And there is the idea of it's called cosmic Darwinism, in that there is a multiverse. And in the multiverse, whenever there is a black hole, you can form another universe. You can do some math calculation that really tells you that if you have a black hole and at the center of that black hole there is a singularity, and the black hole is spinning in a certain way, you could go through the singularity. That's the idea of where the wormhole comes from. You can make the math calculation, it doesn't tell us if it's true. And what we can say about if there was something that comes out of nothing, the way that my favorite idea of to explain that actually comes from thermodynamics. Pretty much, the laws of thermodynamics are the thing that you can never, ever bet against in the universe. Everything else, I think, it's open to interpretation. I am very willing to say even the Big Bang is open to interpretation. Thermodynamics is very, very good. The three laws state that the most important is the second one, but the first one tells you about the energy of a system, how you can turn work into heat, stuff like that. Given that we're in Manchester, that was the crucial thing based on the Industrial Revolution. The second one, entropy always increases in a in an isolated system. That means that the level of disorder in a system is always getting higher. This is why it's a lot more easy to mess up your house than tidying it up. The third one is that you cannot go to absolute zero, the lowest possible temperature, which is minus 273.15 degrees Celsius. But those are, for all of you, were like, okay, you just told us some stuff, but I'm not getting it. So let's hope that you all like to play some, I don't know, card games, some gambling games, some poker. The first law tells you that in the universe, you can never win. You can never get anything from free. You can never get energy out of the universe. The second law, the fact that the entropy always increases, tell you that you cannot draw. You can only lose in the universe. And the third one, the one about the lowest possible temperature, tells you that you cannot leave this table. You are stuck in this universe. And if the entropy of the universe always increases, it will reach, if the universe expands forever, and that is our explanation, it will reach a point in which everything is going to be entropy. There's not going to be anything else. And then things get interesting with quantum mechanics. Quantum mechanics has a weird effect when it comes to entropy. Locally, in small little areas, the entropy, even when it's maximum entropy, can drop. Now, one of this theory suggests, what if everything is in this maximum entropy, that there is all this energy, but you cannot use it, but then a tiny area, a tiny region, suddenly drop in entropy and has energy. So from this vacuum of nothing, of energy you cannot use, suddenly you can grab a little bit of energy and maybe bang, and a universe starts. I like that idea because I like thermodynamics, and I feel that thermodynamics is, so far, 220 years, more or less. Never been proven wrong, so I feel like maybe we can bet on that. But we don't know. Ultimately, we don't know because it's beyond the law of physics.
But if you don't know... Sorry? Okay.
Sorry. So I'm just going to... number 4?
We'll continue later.
I'm passing over to number 4.
All right.
Thanks, Peter.
Yeah, thank you, Alfredo. I'm afraid I have another profound question.
Go for it.
You argue very persuasively that light is central to life and to its origin. The sun is still shining, last time I checked. So why is life not spontaneously forming on this planet, all the time, right? Why do we have to trace it back to a special event 4 billion years ago? Particularly when, and just to respond to the first question, we still have those hydrothermal vents, so we still have those hot springs. They're very similar to how they were, 4 billion years ago. So,
very good question, and I think we can get to an answer there. You're absolutely right. The planet has all the ingredients to make more and new life. The problem is that I think what is special about life, and I hope that is special of all life in the universe if it exists, but it's definitely special about us, is we're very good at competition. All those building blocks that an emergent organism could use to create its own niche, they're taken. They get quickly taken by the living organism that exists now on the planet. Before we got from the first type of life to anything that resemble like the complexity of life today on the planet, it took billions of years. And now, if there was some special molecules that had started to assemble here today in a tidal pool somewhere on the planet, it's competing with organisms that have been here for a very long time, and they really know how to play the game. So that's why we're not constantly finding new life forms. If there is anything that is trying to form, we easily outcompete. But to push your question a little bit further out, what if there are places where that is not the case? I found it very interesting. A few people found it extremely controversial, but I thought it was very interesting. A paper last year that said, let's imagine that we go to Enceladus, and there is a mission, awful mission from the European Space Agency to land on Enceladus by 2050. It takes so long because we need Enceladus to be in pretty much summer and have a lot of sunshine, and this is why it needs to be then. And Enceladus has a little geyser coming out from the South Pole, so even we don't have to dig the 20 kilometers of the ice crust, we can touch the ocean, we can sample the ocean. Let's imagine we find no evidence of life. We have a world that has the right condition, that has the hydrothermal vents, has the chemistry, but let's assume that we find no evidence of life. And the paper asks, should we try to turn the moon into a big experiment and see if we can create, just by putting the little ingredients that we think were fundamental to life on Earth, and see if we can create life? And I thought it was like a really fun paper, because for me it was just like, yes, absolutely. Shouldn't we see if we can? But a lot of people were like, should we be playing God? Do we actually understand if there is life with absolute certainty? But that is exactly that. If there is the right condition, why things are not emerging? Here is because everything is outcompeted. Like even the building blocks, even the simple molecules that will go and make the amino acid for the proteins, etc., just swept up by every other living organism. There's just too much life.
So is there a 5 and a 6, maybe? Can I just ask a quick question of you? I may have this wrong, but yes, I know, but I'm just coming in first, Guy.
Is the mic holder privilege?
I thought, well, I just happened to be holding it. I just thought there were 3 pieces of evidence for the Big Bang occurring. Maybe I'm wrong. So I understand the universe to be cooling and expanding. So if you do the reverse maths, you get back to a point in time, and also the 380,000 years elapsed.
Background.
The plasma cooled sufficiently in order for the electrons to combine with the protons to make the first atoms.
Yeah,
and I thought those were the 3 pieces of evidence that showed the Big Bang occurred.
Yeah, but it's like a very terrible body wash, because it's 3 in 1. It's because on this one, yes, we know that this is the temperature map of the universe, and we can calculate when it was emitted, 380,000 years after the Big Bang. And we can work it out backwards. And so, yes, things are coming in. The other thing is the expansion of the universe, which we can also see through here. And the recombination in the hydrogen, which, yes, but pretty much with this alone, we can tell this is the proof. And to give you very, I don't know what, we're 15, oh yeah, we're 15 minutes, I can tell you the story. So the two researchers that were finding they discover the cosmic microwave background, they were not looking for the cosmic microwave background. They were working for the Bell Lab in upstate New York, and they were testing this microwave system that back then, before we had telecommunication, they were going to reflect microwaves on big spheres in space to do intercontinental telecommunication. And they kept finding noise in the signal. And they were like, the signal shouldn't have this amount of noise. So they look at their antenna, and they thought they found the problem. There were pigeons in it. So they thought, probably pigeons not good for this signal. And so they move away the pigeons. They spent winter scrubbing the antenna from all the pigeon crap, and they measured it again. And they still found the noise. And then they realized that the noise was coming from everywhere, in every direction in space. So they phone their local astronomy department and say, are you looking for a signal from everywhere in space in the microwave region? And they're like, yes. Well, we found it. And that's how they won the Nobel Prize.
You talked about photosynthesis as being essential to the life, but there are animals on this planet that never see any light. They live in subterranean caves or the bottom of the ocean.
Okay, there is an interconnectedness of it all. While we got to the exception, those animals still use oxygen. There are a great example of actually, to be myself devil's advocate, there is a lake in Antarctica that has been sealed off from, I think, 3 million years ago. Double check the number, but it's been a long time, and there's still animals that survived in there. But it's all connected, because the things that make the massive change was the first photosynthetic organism that released oxygen. So there are organisms near the hydrothermal vents that they don't use the oxygen the plants are producing now, but they did evolve from the same ancestor as all the other animals that, all the other, not just animals, all the other beings on the planet. They use oxygen, they use light, even though they might not do it now. And again, the profound question is like, it is a big assumption saying this works here on Earth. Light is fundamental because light leads us to photosynthesis. Photosynthesis led to oxygen. Oxygen led to differentiation, and we're here. We need oxygen. If we don't eat plants directly, we eat animals that eat plants, and so on. Could it be different out there? Could it be beings that don't do photosynthesis, still survive, they use light in different way? We knew that before the cyanobacteria and the great dying, the great oxygenation event, there were microorganisms that were using light in different way. How exactly? Unsure. But it's a complicated question, is the fact that now even those that do not use light directly, do not eat plants, do not, even some that don't need oxygen directly, still benefited of those evolutionary steps that then led them to be like, okay, you know what, I don't need oxygen anymore, I can live in this, I don't know, underground, near an hydrothermal vent, in an acid lake in Yosemite, and do something different. But those organisms only got there through being like the rest of us.
Is there a 5 and a 6? Not all rush at once. Oh yes, okay. You're a 5, Johnny. I'm coming over. There we go.
I'm puzzling over the idea of photons that are virtual and you can't see. So is that a belief system or is it just a probability?
It is not a belief system, but I think that could be one of my favorite questions on that. So it's a mathematical thing that suggested that it should exist, and the reason why are virtual and we cannot see them is the uncertainty principle. So Heisenberg's uncertainty principle put a limit on how much we can know in the universe. Ultimately, it's telling us our knowledge cannot be infinite. But we can, there are a few physical effects that are measurable that can only happen if these virtual photons exist. One of them is called the Casimir effect, and usually I'm sure that there must be plenty of ways to also test it on Earth, but in space has been tested, vacuum space, and you have two metal plates and they're very, very close to each other, and the interaction between the atoms in the metal plates make the two come together. And it's only possible, and I'm trying to remember all the things because I haven't done that in physics in a very long time. So if you want, later we can look it up together, and it's only possible because of the presence of these photons between the two. So they are virtual because we cannot directly go and like pick them out and say, haha, I got this photon, because the interaction is within the remit of the uncertainty principle, but they do have an impact. They do have measurable effects. How are we doing so far?
Thanks, that's
No.
brilliant. It was brilliant. Can I have another one?
Sure.
Sorry, it's the cyanobacteria thing, which is sort of a blue-green algae, isn't it? Mm-hmm. Which my father actually did his PhD on in the 50s, actually.
Oh, cool.
But probably not in this context. I must go and read it now. So should we all have a jar of that under the bed just in case another extinction happens? Because...
To be honest, they caused the first extinction, so I don't know I think
they caused it.
Yeah, because of the oxygen. They produced the oxygen, and sorry, I thought I probably just came too quickly on that. Apologies for that. So yes, they were responsible for the extinction because they created the oxygen, and oxygen is a very reactive element. So they liberated the oxygen, and all the other species, most of the other species, just died. But we're here because of that, and we managed to learn to harness these little fires in our cells, and we can use the oxygen to release energy that we get from the sugars and for consumption of things. So I think if we really want to keep them on our good side, maybe we should not like pollute the oceans and stuff like that, and try to keep them happy, and hopefully they don't cause any more extinctions.
Was there somebody else? Oh,
Can I ask a little thing?
Cool.
What were the creatures that were there before that extinction happened? Was it just bacteria?
Yes,
or?
it would be something very, very simple. This is connected to the resource. It took a long while for anything complex to appear on the planet. There is some argument that actually the oxygen, because thanks to the oxygen we can free more energy, allowed us to become more complex. But those organisms were as simple as possible, even simpler than the modern blue-green algae. So it's like, and we only have traces. Like, we know that happened because we can see the effect of oxygen on the rocks. We don't know exactly when it happens. This is why that has 400 million years of range of when it happened. It's like was it a gradual process, or there was a moment that it suddenly spiked up? What were the changes? There is so much that we don't know, because, and for as much as the ignorance, it's a problem for us science, it's possibly the reason, again, we are here, is Earth is a very active world. The reason why we don't know is because those rocks have mostly changed. The planet has changed dramatically. Some of it is because of plate tectonics, some of it is because of our amazing atmosphere, some of it is because life has changed the planet. So we are stuck on this like, ooh, this is all great because this allowed us to live, but also, oh, and it's not great because we don't know what exactly happened back then.
Is there anybody else? No. So, as I understand it, the great oxidation event also in time built up the ozone layer.
Yes.
And the ozone layer building up enabled bacteria and other forms to emerge from the seas. Yeah, is that right?
Yeah, without
the... Without the ozone layer, we wouldn't be here.
Yeah, the sun releases a lot of ultraviolet radiation, and that is bad in general because especially for simpler organisms, it can just disrupt DNA. It's the same reason why we use SPF, because we want to protect our skin cells from cancer. Why it could create... sunlight can create cancer because sunlight can damage the DNA. When you are a much simpler organism, you have a lot less protection, and those mutation, probably before there was ozone, some of those mutations were advantageous, and some organisms emerged thanks to those. After, it's just like, ooh, no, we have got used to be protected from ultraviolet. No, thank you, we don't want any more.
Yeah. Well, it's almost 9 o'clock. I'm going to declare that the meeting's over. I'm sure we'd all like to thank Dr. Alfredo Carpineti. A huge round of applause for what was a fascinating...
Thank you. Thank you.